Section 2.7 has to do with position vectors. So position vectors just let you know where a particle is located in reference to another location. So let's say we have this bridge and we are interested in, let's say, point A, and we'll call this point B. So if I want to know the position of B relative to A, then I would have a vector that looks something like this. Or it would go from A to B. So this position vector, we can label it as R, and it is a vector. So we know that vectors have both magnitude and direction. The objective for section 2.7 is to determine the I, J, and K components of a position vector. So let's say we're given point A and point B in this coordinate system. And let's say these distances, let's say they're just 4 meters by 3 meters, and it goes down into the Z direction, let's say by 2 meters for position A, or point A, and for point B, let's say it is approximately 1 meters right here, and let's call this 2 meters into the negative Y direction, and it goes up into the positive Z direction, let's say by let's say 5 meters. So we can identify the position coordinates for A as being positive 3. In terms of the Y, it'd be positive 4 and negative 2 meters. And for position B, the coordinates are that it would be positive 1 in the X direction, negative 2 in the Y direction, and positive 5 in the Z direction. So once we have those position coordinates, we should be able to determine the position vector by doing this particular math. So let's say we're interested in the position vector R that goes, let's say, from A to B, right? So from A to B. So what we have to do is take the final position coordinate minus the initial position coordinate. That is, it would be positive 1 minus 3, that would be my I component, plus a negative 2 minus a 4, that would be my J component, and finally positive 5 minus a negative 2, units would be meters, and let me use a subscript from A to B. So my position coordinate, RAB, is given by negative 2I plus a negative 6J plus a 7K meters. You can also interpret position vectors as the distance that one would have to travel from point A to point B along each axis to get to point B. Meaning, starting from point A, we have to move back negative 2 meters, go to the left in the Y direction, negative 6 meters, and go upward 7 meters to finally get to position B. Now recall these formulas from the earlier sections. Since the position vector is a vector, all these equations apply, meaning instead of A, we would have R. We can find the unit vector along a position vector R, and we can define it as the position vector divided by the magnitude of it. What that'll give us is the x component of the unit vector along that position vector. Likewise, we can get the y component of the unit vector along that position vector, as well as the z component, and it remains dimensionless, so no dimension. We can also rewrite equation 2.7, where we have a unit vector along that position vector, and we can define it in terms of the direction cosines. And of course, this equation also applies. What this equation says is that if I have a position vector and I know the magnitude of that position vector and I multiply it by the unit vector along that position vector, it would equal to a cos alpha I plus a cos beta j plus a cos gamma k, which means this is my ax component, this is my ay component, and this is my a. It would equal to the magnitude of that position vector times its direction cosine alpha I plus the magnitude of that position vector times cosine beta j, and same thing for the k component. And this in essence is my rx component, ry component, and rz component. So let me go over what this actually means, the unit vector, meaning if I have a point A to B and I am defining that to be my position vector r, then that unit vector point has a magnitude of 1.0 and it lies on that position vector. So that is u sub r. There is an example in your textbook, example 2-10. I would highly recommend that you review this problem before coming to class. Highly recommend review and work it out yourself. Section 2.8 has to do with finding a force vector directed along a line. Let's say we're given this XYZ coordinate system and there's some kind of bracket on this XY plane. And on that bracket there's a cable. So we'll say that's my cable. So here's my cable. And that cable is being pulled with a force of 500 newtons. And let's say we have some measurement device and we can actually find the position coordinate for point A as well as point B. And let's say for the sake of conversation, those coordinates are 2 meters, 5 meters, and 6 meters for B. And let's say it's 1 meter, 0 meter, and 4 meters for point A. So the objective for this section is this. I want to be able to express this force vector in Cartesian vector notation. So how do we go about doing that? So the objective is to find the Cartesian vector notation for that force F. So in order to find the Cartesian vector notation for this force F, we'll have to use a couple of equations that we've been introduced to in the previous sections. So the first one is this. So I'm just going to write that down here for our reference. And we'll modify it for this particular problem afterwards. And the next one is this equation. So this equation says that for a given force vector A, it's equal to the magnitude of that force vector multiplied by the unit vector that lies along that force vector A. So for this problem, we have a force vector that we are interested in finding the Cartesian vector notation for, and that would be equal to the magnitude of that force, which we know to be 500, and we want to multiply it by the unit vector that lies along that force F. So we're going to use a subscript F. Next, what we're going to do is use this equation and modify it for this particular problem. So the unit vector along force F is equal to the position vector that goes from A to B. So what we're doing is we're utilizing this information that we have. Once we have these position coordinates, we know we can find the position vector, which we can use in this equation to get our unit vector. And that is simply equal to, so this position vector RAB is simply 2 minus 1 I plus 5 minus 0 plus 6 minus 4 K meters, all divided by the magnitude of that, which would be 2 minus 1 squared plus 5 minus 0 squared plus 6 minus 4 squared. That would also have the unit meters. And that simplifies to 1I over, and if you do the math for this denominator, it comes out to 30 plus 5J over radical 30 plus 2K over radical 30, and it's dimensionless. So that is the unit vector that lies along this line. So now all we do is substitute this back in here. F is 500, so we have 500 times all of this, 1I over radical 30 plus 5J over radical 30 plus 2K over radical 30 newtons, and this is the Cartesian vector notation for that force F.